Hi everyone. In the previous lecture, I covered just a sampling theorem statement. So now let us see the mathematical steps involved in sampling theorem proof. So what was the sampling theorem statement? To convert any continuous time signal into discrete time domain signal, when a principle has been given, that is sampling theorem, right? So what was the condition? What is the criteria there? Fs must be greater than or equal to twice that of maximum frequency component. If we represent it using omega means this is nothing but omega is nothing but maximum frequency component present in the given input signal. Problems are also important based on sampling theorem principle. So what is this twice that of highest frequency component is known as Nyquist rate. Nyquist rate. Nyquist rate is nothing but twice that of highest frequency component present in the given input signal. Okay. So the statement we discussed, now we have to study about the proof. So while discussing the proof, mathematical equations will be there along with the graphical representation. So first we write mathematical representation and corresponding graph. If we have mathematical equation, then only we can sketch the signal, right? So let us see the proof now. Put the heading proof. So in three cases will be there in the proof. When fs equal to 2 omega, what happens? When fs greater than 2 omega, what happens? When fs less than 2 omega, what happens? As I already said, if fs is greater than or equal to 2 omega, then only perfect reconstruction is possible. That means after converting it into continuous time domain to discrete domain, we can recover our original input signal if our sampling frequency is greater than or equal to twice the highest frequency component. So the minimum sampling rate required here is known as Nyquist rate. What was the minimum sampling rate required here? 2 omega, nothing but Nyquist rate, because this is known as Nyquist rate. What was the condition? Fs greater than or at least equal. So that minimum condition is Nyquist rate. So the minimum sampling rate, F minimum, is nothing but Nyquist rate. Okay. Nyquist rate, that is nothing but uh, 2 omega, twice that of highest frequency component. So before starting the proof, just to put the heading proof. So first you write the statement. We have to take the input signal. We have to derive the equations. Then we go for three cases. First we have to derive final mathematical expression. Then we can go for different cases. Just we need to substitute when f is greater than 2 omega, those three conditions. So now let us see the first one. So what was the condition? This sampling theorem is applicable only for band limited signals, right? So in the proof first, let us consider x of t, which is an analog signal having a finite energy. Finite energy must be there. Finite energy, and its band is limited to omega. So what I'm saying, consider x of t is an analog signal having a finite energy and its band is limited to omega. That means the maximum frequency component present in this signal is omega. So beyond omega, there is no other frequency component in the given input signal. Then what is the restriction on fs? Then fs must be greater than or equal to 2 omega. Isn't it? When fs greater than 2 omega means what happens? What about sampling interval? Ts must be less than or equal to 1 by Nyquist rate or Nyquist interval. Nyquist interval means what is Nyquist rate? 2 omega. Nyquist interval means 1 by 2 omega. Okay. So this is known as sampling interval, sampling period. Okay. So consider x of t is an analog signal having finite energy and maximum frequency for component omega. That means it is band limited to omega. Then fs must be greater than or equal to 2 omega. First write this statement. After that, now we have to draw the signals. So as I already said, x of t is a continuous time domain signal. So the signal may be of this form. Okay, maybe the duration, whatever may be the duration. Let us say minus t1 to plus t1. Okay, this is t in second, continuous time domain signal. And this is band limited to omega. Means its spectrum is going to be like, let us assume this is its corresponding spectrum. or what we take generally, f is the frequency component we take, right? So let us take here f, because maximum frequency component fm you can take, or omega I have given. So I'll take it as omega minus omega 2 plus omega, and it's a spectrum x of omega or x of f. Both the representations are same. X of f versus f. This is its corresponding frequency domain representation. We are assuming that this is band limited to omega. So beyond omega, there is no other frequency component, all zeros, isn't it? So this is the corresponding frequency domain representation of given input continuous time domain signal. So you can take this as figure 1 and this as figure 2. So you can write the statements like figure 1 shows the given input signal and figure 2 shows the spectrum corresponding to input signal x of t. Now to convert this x of t into discrete time domain, what we do here is take a train of impulse function. You can write the statement also here. Take a train of impulse function which are located at regular intervals of sampling period. Take a train of impulse function, already we discussed in Fourier series concept. Okay, now try to sketch the sequence. Train of impulse function t equal to nts here, which are located at, impulses are located at regular intervals of time, and we represent this as delta ts of t. Delta of t is a impulse function, impulse signal. Delta ts of t means train of impulse function. Look, this amplitude is 1, right? All the amplitudes. Train of impulse function located at regular intervals of time. This is 2s, 2ts, 3ts, so on 4ts, like that. And here also minus ts, similarly. Same amplitude, uniform amplitude, minus 3ts, minus 2ts here. So like this is the train of impulse function. You please write it properly. Same amplitude. Same amplitude must be there for all these samples. This is the train of impulse function located at regular intervals of sampling period. What is the sampling period here? Ts. Ts is our sampling interval of sampling period. So the corresponding mathematical representation for this delta Ts of t here is, how do we represent delta Ts of t means Fourier series concept. How to get the mathematical representation for any periodic signal? Fourier series. Fourier series itself application is for periodic signal mathematical representation. So using Fourier series, we can this graph complete train of impulse function can be represented as summation n equal to minus infinity to plus infinity delta of t minus nts. So this is train of impulse function mathematical representation. Okay. Important. Without having these mathematical equations, further we cannot proceed. So this is very easy, right? At t equal to, for example, n equal to minus infinity to infinity. N equal to 0 if you take delta of t here at origin. If you take t equal to n equal to 1, and if you take n equal to 1, t minus ts. N equal to 1 means t minus ts. Delta of t minus ts at n equal to 1. So this function exists only when this inside term is 0. When this inside term is 0, at t equal to ts only. At t equal to ts, delta of 0, amplitude is 1. This is at t equal to ts. We are adding, summation is there. That's why this is a train of impulse function. Okay. So please go through this proof if you have any doubt. This is its corresponding mathematical representation, train of impulse function. If you have any doubt, we will discuss this mathematical representation also. How do we get this using Fourier series? That one more video lecture I'll discuss. There I'll discuss. Now the logic is, first I have taken one input signal. After that I have taken a train of impulse function. Next what we have to do to get the continuous time domain signal means multiply the input signal. Multiply this input signal with the train of impulse function delta ts of t. These two signals we have to multiply. If you multiply these two signals the final resultant signal is going to be like t equal to nts only here, integer at sampling intervals. So whatever amplitudes are there, all these amplitudes are existing only at ts, 2ts, 3ts, 4ts, so on, right? Similarly here also minus ts, minus 2ts, minus 3ts, like this. So at t equal to 0, what is the amplitude here? All the amplitudes are constant, that is 1, isn't it? And whatever amplitude is there at t equal to 0, that amplitude is multiplied over here and we will get that amplitude. Next at t equal to ts, what is the amplitude here? This amplitude. Whatever may be the amplitude, it is multiplied with 1. Same amplitude we will get. Next at t equal to 2ts, whatever amplitude is there, we will get this. So same envelope we will get. Same envelope we will get. But in the form of samples at t equal to ts, 2ts, 3ts, 4ts. We are extracting samples which are located at whatever envelope is there, same structure we will get. But at in between 0 to ts, there is no amplitude. Zeros are there. Zeros are multiplied with this. This part will be eliminated. Next at t equal to ts, 1 is multiplied with this 1 amplitude. That corresponding amplitude will exist here. So we are multiplying corresponding amplitudes which are located at regular intervals of time, ts, 2ts, 3ts. So this is a final spectrum. What we are going to get here also amplitudes. So this is finally resultant signal, that is after multiplying, we represent this as x delta of t, x delta of t. How we got this? X of t is multiplied with delta ts of t, multiplication of these two signals, x delta of t. This is resultant signal after multiplying your input continuous time domain signal with train of impulse function. Okay, after multiplying train of impulse function, this is our resultant signal. So now we have to do, this is mathematical representation, input signal, train of impulse function. After multiplying these two, resultant signal, and we got only mathematical expression for train of impulse function. This is a train of impulse function, Fourier series representation, mathematical representation. So now we have to discuss these graphical representation in mathematical form. Okay, I'm erasing the content. Now try to represent these in mathematical representation, graphs and all. It's taking a lot of time. Clear whiteboard is not there. Okay, just a minute. So now let us see the mathematical representation. After multiplying those two signals, resultant signal we have seen. Now let us see the mathematical representation. So the sampled signal, whatever we got x delta of t, that is known as sampled signal. X delta of t, which is nothing but x of t into train of impulse function delta ts of t. So this is known as sampled signal in time domain. Sampled signal in time domain. Okay. So you can take this as equation 1. Graphical representation already we discussed. The sampled signal can be mathematically represented as follows. You can write here the sampled signal can be mathematically represented as follows. Graphical representation already we have seen, like first we have taken input signal, train of impulse function. After multiplying, we got the resultant signal, that is sampled signal in time domain, isn't it? So now let us see the mathematical representation. So here x of t, and what is the corresponding mathematical equation we are having for train of impulse function? N equal to minus infinity to infinity delta of t minus nts, isn't it? So here summation n equal to minus infinity to infinity x of t, we can take this inside delta of t minus nts. Okay, but as I already said, in x delta of t on x-axis t equal to nts only, t equal to nts. For remaining values of t, there is no amplitude, its amplitude values are zeros. So this exists only at t equal to nts. So we write this as n equal to minus infinity to infinity x of nts into delta of t minus nts. So equation 2 represents ideally sampled signal in time domain. Okay, even here also you can write x delta of nts also, but which represent it is a time domain, t equal to nts. This equation exists only at t equal to nts. X of t is defined at each and every instant of time, but to extract its samples only, we are taking a train of impulse function which exists only at t equal to nts, where n is varying from minus infinity to infinity. Hence, this product exists only at t equal to nts. That's why we have replaced t with nts. X delta of t. What is x delta of t? Sampled signal in time domain. Finally, this is a mathematical representation for sampled signal in time domain. Right? Take it as equation 2. So equation 2 represents ideally sampled signal. Whatever technique we used here, that is known as ideally sampled signal. Even in sampling, we can take the samples using 3 different methods are there. This is the first basic method to convert continuous time domain to discrete time domain signal. What we did here in the procedure, we have taken input signal, we have taken a train of impulse function, next we multiplied, right? So this multiplication procedure, multiplying input signal with train of impulse function, is known as ideal sampling technique. So this equation 2 represents ideally sampled signal in time domain. You can write the statement here. Equation 2 represents ideally sampled signal in time domain. So to prove this, as I already said, 3 cases are there. No, Fs greater than 2 omega, Fs less than 2 omega. There we are dealing with frequency component. Fs less than 2 omega, what happens? Greater than 2 omega, what happens? Equal to 2 omega, what happens if sampling frequency? This equation, sampled signal, is in time domain. So, whereas here the conditions are in frequency domain. So this equation 2 has to be converted into frequency domain. That means whatever this ideally sampled signal is there, that we have to discuss now in frequency domain. Okay, so you can put the heading frequency domain analysis. Okay, frequency domain analysis. Put the heading frequency domain analysis. So whatever first signal is there, write as it is. The sampled signal in time domain is defined as x delta of t, x of t, summation n equal to minus infinity to infinity, delta of t minus nts. You can write it inside also. That equation is correct only. Now why I am separating it means to use the property of Fourier transform, because here 2 signals are multiplied. Okay, convolution theorem is there, multiplication theorem is there. I discussed in Fourier transform properties concept, second unit. Please go through that lecture. So we have to apply Fourier transform on both the sides, right, to discuss in frequency domain. So you can write here inside also like x of t into delta of t minus nts. Then also we have to take it outside x of t to apply Fourier transform, because directly we cannot use the Fourier transform formula to convert extra delta of t into x delta of f to convert it into frequency domain. We have to use properties. To use the properties, we have to arrange the terms depending on property application. Okay. So here Fourier transform of x delta of t, small x delta of t is nothing but Fourier transform of x of t multiplied with Fourier transform of this function n equal to minus infinity to infinity delta of t minus nts. Okay. So now we have to use property. So do you all remember convolution theorem is there as well as multiplication theorem is there. Convolution theorem states that if two signals are convolved in time domain, then corresponding spectrums are multiplied in frequency domain. Similarly, multiplication theorem states that if two signals are multiplied in time domain, if two signals are multiplied in time domain, then the spectrums are convolved in frequency domain. So here signals are multiplied in time domain. So we cannot separate it like this. So initially we have to write Fourier transform of this total signal. Please understand here. I'll write one more step, then you can easily understand. So I'm erasing the content here. So if you apply Fourier transform on both the sides, this is nothing but Fourier transform of x of t into summation whole signal I am writing first. Delta of t minus NTS. Fourier transform of these two signals which are multiplied in time domain. From the multiplication theorem, if two signals are multiplied in time domain, then the Fourier transform is convolution in frequency domain. That is the theorem statement. If two signals are convolved in time domain, then Fourier transform is individual spectrums are multiplied. If two signals are multiplied in time domain, then Fourier transform is individual spectrums are convolved in time domain. So from this multiplication theorem, now this changes to, please go through the multiplication theorem statement if you have any doubt. Convolution, not direct multiplication. Individually, not multiplication is not possible. Convolution. This is convolution symbol. Convolution of first signal. It's a Fourier transform of second signal. If two signals are multiplied in time domain, then corresponding spectrums are multiplied in frequency domain. If two signals are convolved in time domain, then spectrums are multiplied in frequency domain. Those are the statements of multiplication and convolution theorem statements. Like this. Okay, this is convolution property and multiplication theorem property statements. Here we are using multiplication theorem. Please remember that. Okay. So here, what is the Fourier transform of x of t? It's nothing but x of f, standard representation. And x of f is convolved with Fourier transform of delta of t minus nts, summation n equal to minus infinity to infinity. Periodic signal. Fourier transform of periodic signal is different from normal periodic signal. So if you see here, summation n equal to minus infinity to infinity delta of t minus nts. Its Fourier transform pair is fs into summation n equal to minus infinity to, I'll write here down. Otherwise, I'll write here only. Just a minute. Please important point this. Make a note of it. Summation n equal to minus infinity to infinity delta of t minus nts. Its Fourier transform is fs into summation n equal to minus infinity to infinity. Okay, delta of t changes to f, time variable changes to f, and nfs. Important. Fourier transform of a periodic signal. This is using Fourier series concept we derived, and this is Fourier transform of a periodic signal concept. From that concept, easily you can derive this Fourier transform. Okay, please make a note of this. Fourier transform of a train of impulse function. Summation n equal to minus infinity to infinity. Delta of t minus nts is in Fourier transform pair with fs. Fs is nothing but 1 by ts. Fs into summation n equal to minus infinity to infinity delta of f minus nfs. Now we have to substitute this here in place of this. Okay, in place of this, we have to substitute here. So if you substitute it, here what we are having Fourier transform of on left side x delta of t, right? Fourier transform of x delta of t. What happened is, okay. So here we are discussing in time domain to frequency domain, right? X delta of f. X delta of f is equal to x of f convolved with fs summation n equal to minus infinity to plus infinity delta of, just I have substituted train of impulse function Fourier transform. And fs is constant here. It is not at all depending on frequency variable. So you can write it outside, fs outside, and x of f is convolved with summation n equal to minus infinity to infinity delta of f minus nfs. Okay. Now from the properties of impulse function, any function convolved with impulse will give the same function. Means x of t convolved with the delta of t will give you the x of t only, but at t equal to 0. Because delta of t exists at t equal to 0 only, right? Similarly, any function convolved with impulse function, from the properties of impulse function, please refer that video lecture from unit 1. Fs will give the same function with which we are convolving. Okay, x of t only at t equal to 0. Here in place of f, what we have to write? This one, f minus nfs. You can also write x of f where f equal to f minus nfs, like that. Okay, so because a delta of t defines at t equal to 0 only. When this becomes 0, when f equal to nfs. So similarly, like t equal to nts, here also f is equal to nfs. So any function convolved with impulse will give us the same input function. So that's why here x delta of f equal to fs into x of f minus nfs. This is a sampled signal in frequency domain representation. And one more thing, I forgotten here, summation, because x of f convolved with delta of f minus nfs. Summation will be there as usual. Summation n equal to minus infinity to infinity, where f equal to nfs. This variable f equal to nfs. Fs into Fs into summation n equal to minus infinity to infinity x of f convolved with delta of f minus nfs. So, which gives the same spectrum, original spectrum, but at the intervals of impulse function f minus nfs. So this is the expression 1. Equation 3 you can take. Equation 3, which represents the ideally sampled signal. This is nothing but ideally sampled signal in frequency domain. So which is also a periodic spectrum here. This is also a periodic spectrum with the period is equal to sampling period. With the period f equal to nfs, I'm saying no. NFS means fs. Fs is a sampling frequency. So with the period is equal to sampling period. Sampling period means Ts. Okay. Sampling frequency means Fs. So these are the equations. Equation 1 represents the time domain representation of sampled signal, isn't it? Equation 2, three equations we wrote now. X delta of t equal to x of t into delta ts of t is our equation 1. Equation 2 represents ideally sampled signal in time domain. Equation 3 represents ideally sampled signal in frequency domain. Please write this statement also. The above equation, that is this x delta of f is also a periodic spectrum. This is a periodic spectrum with the period is equal to sampling period. With the period equal to sampling period. Now here we have to substitute the three condition. When fs greater than 2 omega, fs less than 2 omega, equal to 2 omega, what happens? So this is about sampling technique. Now we have to see the three cases. All these equations, derivations will come under proof only. Three types of sampling techniques are there. That we will discuss in the concept types of sampling techniques. Here, one of the techniques we use, that is ideally sampled signal. What is meant by ideally sampled signal means multiplying x of t with train of impulse function. That is the logic we used here to convert continuous time domain signal to frequency domain. So we have seen the spectrums, not spectrums, like time domain signals x of t, train of impulse function, isn't it? First x of t I have taken, delta ts of t I have taken. After that, I have multiplied these two signals. Then I got time domain sampled signal. After that, frequency domain analysis we have seen, isn't it? So finally, this is the equation what you have to remember to substitute the three cases, case 1, case 2, case 3, that I will discuss in next lecture. Okay. So thank you all.